Okay, this is lab number 10, choked flow, and we'll be dealing with compressed fluids. You've been provided with this lab report and also with the tank blowdown math that accompanies it, and you should have taken the time to read through these. If you haven't, please read through these documents carefully, the whole thing, and then review the different parts with your group so that you know what you will be doing in this lab experiment. So go ahead and pause the video for a few minutes and read through this and discuss with your team. Okay, so there's a safety section which you should carefully read, some background information, and then a pre-lab preparation with some questions. First thing we want to do is familiarize ourselves with the different components of the lab. There's several parts: a black-orange flow control knob on the building compressed air supply, a mass flow meter on the supply line, a small black-red flow control knob, the pressure gauge on the tank, 4 outlet orifices on the tank, these have different sizes, and then 2 pressure relief valves with pull rings. And so we'll switch over to the camera here and kind of walk around and show the different parts. And then I want you to pause the video and make sure that you can identify all the parts and what's happening with your group, and then I'll explain them in a little bit more detail. Okay, so go ahead and pause the video and make sure that you can understand and identify each of these components A through F on the lab setup and what you would need to do to start those. Okay, so as we look at the unit, we have the black-orange flow control valve at the wall here that controls the air. That flows through a pipe in the back which comes around here to this flow meter, and it's reading flow rate at standard temperature and pressure, and then it wraps around and comes through this manual control valve that we can change, this black-red control valve, and on into the tank. And we have a pressure meter on the tank. We turn it on and it's reading PSI gauge, and then we have these 4 orifices, and we're going to measure the discharge coefficient. There's 2 on this side and 2 on this side, and they have different sizes. This is the big one, this is the small one, and then the back 2 are intermediate size. And then on the top we have a pressure relief valve and another pressure relief valve here. And we can pull these to make sure that the tank is fully empty, which it is. You can also see that as the pressure gauge is reading 0 PSI. So we're going to do 2 different things in this lab report. The first is going to be to fill the tank and calculate the total volume of the tank. We're going to estimate that, and we'll do that by, this is item number 3, and we'll do that by starting with an empty tank. The gauge pressure is 0, and then opening the flow control valve very quickly and adjusting it to get to 20 standard liters per minute flow rate. We'll start a stopwatch at the same time, then we'll continue to adjust the knob to maintain it at 20 standard liters per minute. Once we're no longer able to do this, once the tank is full, we'll need to we'll close the valve and stop the time, and we'll record the filling time and then the final tank gauge pressure. From that and the mathematics that are presented in the other document, you can estimate the final tank pressure, and then you can also estimate the tank volume in liters by using a mass balance from the above data. So let's go ahead and do that. I'm going to start a stopwatch, and we're going to open this valve to 20, and then try to keep that at 20 psi, or sorry, 20 standard liters per minute flow rate. There we go. Now as it fills, you'll notice the flow rate starts to drift slightly downwards, so we're going to open that valve a little bit to increase the flow. And the pressure is currently 15 psi. It'll get up to around 70 psi. To 20 psi. Really small adjustments are needed. You don't need to turn this valve very much. PSI. 30, 33, 40 psi. PSI. And I have to make larger and more frequent adjustments as we start to fill this. It's 60 psi now. Constantly opening that valve. PSI. And we'll stop there, stop the timer, close the valve, and the pressure is 74.6 psi. And then we can record the corresponding time. Now we'll notice that the pressure gauge as we watch this is decreasing. This is not a problem with the pressure gauge, so you want to think about as one of the questions why the pressure in the tank is continuing to drift downwards as time goes on. What are the different things that could cause this pressure to be decreasing? So go ahead and work through this problem number 3 with your group, and then we'll move on to question number 4, which is going to determine the discharge coefficient. So you can pause the video here and work through question number 3. Now for question number 4, we're going to determine the discharge coefficient for at least one orifice under choked flow conditions. To do that, we need to determine the mass flow rate through the orifice for a given upstream tank pressure. This is best done by setting up a steady state condition in which we're filling and emptying the tank at the same rate, so that the flow meter on the tank inlet is telling you what is going through the orifice. This should be done while maintaining the tank at high pressure and the orifice at a high flow rate so that choked flow prevails and the digital measurements are more accurate. So we need the tank to be at steady state or we're not going to get accurate results. So you need to think about how will you know if you've achieved a steady state in this experiment. In other words, what physical evidence will you use to determine this? Okay, so let's go back to the tank and look at this device. The only thing we can really change once we open one of these meters is the valve, and we want to get a steady flow rate on the flow meter. But we also want to make sure that the tank is at steady state. So think about what other thing you need to verify and check to make sure that you get at a steady state. Go ahead and pause the video here and talk with your group about this, about what you're going to do to make sure that you're at a steady state. Okay, so I'm going to go and work with the smallest orifice, and I'll go through and do this for each of these and provide you with the data. But I'm going to open this orifice valve and then change the flow rate. I'm going to try to maintain the pressure at about 70 psi and then change the flow rate through the device so that I get a constant flow rate. Now for me, I'm going to use my steady state criteria as the pressure in the tank. If the pressure in the tank is constant and the flow rate going into the tank is constant, and I've waited a while for things to equilibrate, then I can be fairly confident that I've achieved steady state. So once everything has stopped changing, we're going to call that our steady state. So I'm going to open the valve, and the pressure starts to drop. As the pressure drops, I'm going to open this valve. Okay, so I'm at 70 psi, and the flow meter's reading 13.7, 13.6, 5 more, dropping. We're not at steady state yet. Closing that valve just a little bit, because I don't want the pressure to drop. It's a little higher, it's at 71 right now. Let's close the pressure down a little bit. We have 11.6, flow rate 71, 7170. Okay, the valve is now closed so that we have a flow rate of 11.4 until 10, and our pressure is at 70.8, 71. So let's just go ahead and watch this for a moment. Pressure seems to be pretty constant at 70.8, 70.7, and my flow rate is 11.5. Neither of those numbers seem to be drifting too much. So let's call it a flow rate of 11.5 and a pressure of 70.8 psi. .8 psi and 11.5 flow rate, and we'll call that our values. Now we can go back through and repeat this for some of the other orifices and calculate the corresponding discharge coefficients, and the data will be provided for you. So with that, you can go through and work through the other questions in the lab report, and we'll stop there.